Thank you so much. And thanks to everyone at Osler for inviting me to be a part of this conversation. It's a total privilege to be able to talk to people who are out at the frontiers of creating knowledge and really changing the way communities and research are working. Um, uh, and I thought maybe we could start by if Brandon, I could get you just tell a little bit of the story of your educational journey, how it led you to oncology research and where you are now and the things that are really driving you in your career and your research.
Yeah, for sure. Well, thanks, and Patchen, I echo your sentiments, and I just want to thank everyone for having me here today and for coming to attend this talk. It's been a real whirlwind journey, and excited to get to share this story with the Osler community. So I grew up in the Toronto area, just north of the city of Toronto. I was always interested in science from a very young age. I was, my parents could tell you I was taking things apart in the house all the time just to figure out how they worked. Moving through school, I was always very much focused on science, and I really liked biology was my favorite. Um, some of the science teachers had difficulty taking care of me in school because I was always up to this and that. Um, Eventually, I did find genetics as this really cool and interesting field. At that time, CSI was a really popular show, and Horatio would always put on his sunglasses at that key moment, and it made genetics seem incredibly cool. I ended up at going to university at Western Ontario in London, and I found out that they had a genetics program there, so I signed up. And I loved all the genetics problems that we were working on. And I actually also worked at the University of Toronto, Mississauga. We were doing some fruit fly genetics at the time, which was really, really fun. And I learned a ton about the field there. But I was always drawn to cancer, as this seemed to me the most challenging problem that you could ever try and solve in all of genetics. And so I was really drawn to that, and it just seemed really complex. There were people all around the world trying to tackle this issue. And at that time, in the late 90s, early 2000s, there wasn't a lot of headway that was being made, but it seemed that with the developments in genetics, the elucidation of the human genome, and these new technologies that help us understand DNA, that we were really going to make a contribution and sort of crack this code on what I thought was the most difficult to treat and challenging disease in the history of all humankind. My mentors in genetics at that time, they said, well, why don't you go into medical school? Because that's the only way they're going to let you work on human patients. And I did. Moving through medical education, I was really, really happy when I found out there was such a thing called laboratory medicine. In my class, there were about 200 of us studying medicine, and a handful of weirdos from the back of the class will choose to go into laboratory medicine. It's a little bit off the beaten path, and but I've met some truly amazing individuals within the lab. So some of us are quirky and weird, and some of us are just brilliant and with a lot to contribute. But we are hidden away to a degree. We don't see a lot of other doctors on a regular basis, and we certainly don't ever see patients as a part of their regular journey. So I joined that field of laboratory medicine and have been there ever since. I've been practicing now in the lab for over a decade, and eventually made my way back home to the Toronto area, where I live now, and have been practicing at William Osler for the past 7 years or so in our lab at the Brampton Civic site.
So it's such an interesting situation to be in where you're both at the very forefront of this branch of research where you can just transform health and cancer care. But at the same time, you're just a little bit removed from what people imagine when they think about the field of medicine more generally. And One of the things that I've been hearing about that I know is part of what you work on as a lab researcher is this idea of the phrase is next generation sequencing technology. And I wonder if you could talk a little bit about what that is, why it's like, what was the previous generation and what is next generation, and what that means in terms of the potential, how it affects the potential of the kind of research that you're doing.
Yeah, great questions for sure. And you know, I think that a lot of people have the same questions. So here's my take on this. We've known about DNA, in my opinion, for centuries. Even Charles Darwin knew there was probably this material inside of us that could be inherited and passed down from generation to generation. We started to really figure out exactly what that chemical was in the 1950s. And in the 1960s, we had the first method available to sequence that DNA. So to take it from a chemical in a tube and write down the actual words on a piece of paper and start to analyze them with computers or by hand or whatever we're doing. That technology invented in the 60s to sequence DNA is called Sanger sequencing. And that is really the original generation of gene sequencing. When we first started moving into the Human Genome Project in the late 90s, we were using that original technology. And to consider this, the first human genome took us over 10 years, cost $1 billion, and required cooperation from labs all around the world. That's old generation technology. Using new generation technology or next gen sequencing, we can sequence a whole genome in one day for $1,000. And it's basically just a combination of a gene sequencer, the same one that was invented by Sanger in the 60s, together with a high throughput computer. And the computer basically powers that gene sequencer so that it can go really, really fast and do what human beings were doing by hand for many decades prior.
I remember writing about the possibility of the $1,000 genome maybe 10, 15 years ago. And at the time it was a thing that we knew was coming, but it still felt kind of unimaginable at that point. So for it to get to a place where it is reality, almost a commonplace, and in that amount of time is just mind-blowing. And so with that speed of advance, tell me what that means in terms of understanding cancer, in terms of risk assessment, in terms of diagnosis, in terms of treatment. Like what can you do with this now?
Yeah, again, great question. So when I trained to be a laboratory physician, the number one tool that we used was the microscope.
Hmm.
It looks really cool and very sophisticated, and when you have it in your background, it makes you seem very intelligent when you're doing these talks for sure. But the microscope was invented in the late 1800s, and not a lot has changed with that technology. So before the microscope was invented, laboratory doctors would take organs or whole patients. We would look at them, feel them, weigh them, smell them, touch them, even draw pictures of them. And that was the extent of our science. When the microscope was invented in the late 1800s, we could see for the first time what cells looked like. And it was at that time that we realized that a cancer cell looks slightly different than a normal cell. They're funny shaped, they're crinkly, they're a little bit abnormal, their architecture is somewhat disturbed. And all of that visual assessment that we make through the microscope is what gave rise to the next 100 years of cancer research. We learned that breast cancer cells look a little bit different than lung cancer cells, look a little bit different than colon cancer cells, and really used that to help hone the fight against cancer. And that made us very effective guide for surgeons. In fact, I'm an anatomic pathologist, but one of the other names for our field is surgical pathology. So we could tell a surgeon if cancer was benign or malignant. And if it was malignant and they removed it, we could tell a surgeon if they got it all, if the margins were clear. And that was really the major basis for having a laboratory doctor inside of your hospital. But now we're in the midst of another revolution. And the way the microscope changed medical practice forever the invention of next generation gene sequencers is also changing medicine forever. It's a little bit hard to appreciate, but we are inside of a revolution right now. And instead of just looking at what a cancer cell looks like, what it appears like, and its external features, we can use gene sequencers to see what's actually going on inside of the cancer cell. And when we elucidate that information and communicate it to an oncologist in a way that they can understand, then our treatments actually don't target what a cell looks like, but they target the exact problem that made the cell cancerous in the first place. And by attacking that gene mutation, our therapies are a lot more effective. And they're also a lot more easier on patients. They have fewer side effects and they're easier to tolerate.
Can I ask just to clarify a little bit about that? When you're doing genomic sequencing of this, is it a combination of sequencing patients' standard genome plus sequencing the cancer cells in their bodies to identify differences and that sort of things? Or is one of those more the focus than the other, or how does all of that work?
Yeah, so we're born with a set of DNA. We get half of it from our mom and half of it from our dad, and that carries us through our whole life. If we get cancer, some of the cells in our body will acquire new mutations. We can get those from UV light in the sun or from tobacco smoke or just unfortunately bad luck sometimes. And if some of those cells get mutated, they will grow up into a tumor, and the DNA inside of that tumor will be slightly different than the DNA that's in the rest of our bodies. So, what we need to do is get at that cancer DNA. And the traditional way is by taking a piece of the tumor that's been removed by a surgeon or a smaller piece of the tumor that's been sampled by a radiologist or another clinician called a biopsy. And we'll run our gene sequencing on that small piece of tissue. We want to look for mutations that are only present in the tumor and not present in somebody's healthy background cells. And that way, when we prescribe one of these targeted therapies, we know that that's only going to be attacking the tumor cells and won't have any effect on the benign background cells. And that's why these treatments have a much more favorable side effect profile, and the patients are able to stay on them for a lot longer.
And is that where you see sort of the greatest potential for genomic analysis to improve cancer outcomes is in kind of targeted treatments that are specific to an individual patient's cancer tumor's genetic makeup?
I think that was the original hope, is that we can use this technology to prescribe better treatments. But for me, it's just represents so much more. It's a whole new way of thinking about cancer. It's a whole new way of classifying these diseases. And when you use this technology well, we can use it to make better diagnoses, um, better treatments, as you mentioned, but also risk stratify patients, figure out who might get cancer, even make attempts to try and prevent cancers from ever occurring. So this is a tool, and it can be deployed in any stage of the cancer journey, not just the treatment decisions.
Can I just ask you to elaborate a little bit more on what how this technology might lead to better prevention as well? Like what sort of interventions could there be before cancer ever has a chance to manifest?
Oh, absolutely. So, for starters, what we tend to identify cancers when they're advanced. Certain tumor types, especially, lung cancer is one of the diseases that we specialize in here at William Osler. Lung cancer is the number one cause of cancer-related death for Canadians. It's the number one cause of cancer-related death for Canadian women. It's actually a women's health crisis. There more Canadian women die of lung cancer than breast, colon, and pancreatic cancer all combined. So with that disease, and it's a very nice model for some of the work we do. we really need the genetic treatment to come, or the genetic testing to come up with the best possible treatment when a patient's cancer is disseminated and spread over the body. That's been known for about a decade or so. What we're now using gene sequencing for is to help stage a patient, tell whether or not they might be more amenable to curative surgery, and we're even using that to help efforts like screening. So screening is where we might go check ourselves to see if we have a cancer and detect it at an earlier stage when treatments are easier. William Osler actually had one of the first lung cancer screening programs in the country, right here in this hospital. It's only in the past 1 or 2 years been shown to be a very effective strategy, but our thoracic surgery team, led by Kashif Ershad and Mark Ossip, actually started a screening program many years ago. And so that's been going on at Osler and is actually the subject of another very successful research study, which is going to be presented at this year's World Congress on Lung Cancer in September. But the screening has been a very effective way for us to detect these patients earlier. And having the gene sequencing available right in-house actually helps us make that diagnosis at an earlier stage and recognize those tumor cells that might not even be visible just using a regular microscope, so that patients can be more amenable for a curative surgery rather than a treatment that's just going to try and extend their life. We can make this cancer go away for good.
Wow.
Other ways that the gene sequencing can help prevent a cancer would be more in the hereditary space. So if we know a patient's at risk for colon cancer or breast cancer, then we can actually recommend they go for increased screening, so that we'll get them at an earlier age than the public system would normally take them up.
And you can do this at a more granular, more sophisticated level through genomics than just uh, a questionnaire on someone's family history and that sort of thing.
Absolutely, yeah. So every day we understand more and more about how to treat these mutations when we find them. Hereditary genetics is not something that we ventured into just as of yet in William Osler, but I think that like begets like. And since we've started practicing genomic medicine, we have the right tools, we have the right individuals that we can start moving this into other fields, like moving away from solid tumors to hereditary genetics, even cardiogenetics to predict patients' risk of heart disease, like myocardial infarction or hypertrophic cardiomyopathies.
Hmm. Wow. I want to ask a little bit more about um, uh, Osler, the Osler Research Institute is exceptionally embedded in its community, and I wondered if you could talk a little bit about you're doing inherently interesting, groundbreaking research, but why does it matter that that's happening at an organization that's so connected to its community?
Yeah, I think that's really integral to the work that's being done here at Osler is that connection, the location, and the physical space in which we're working. Um, any of the research that our team does within our group is not really intended to generate publications or advance knowledge. It's really has the primary goal of treating our patients better right now. So we're not looking to learn something and do better 10 years from now. We want to provide the best possible treatment to the patient who is sick today. And so any research project we engage in has that primary goal of improving healthcare for you, for the patients who are sitting in the hospital today. When we first started, maybe around 2017 or so, the state of precision medicine in not just William Osler, but in any community hospital in Canada was it was unfortunate. And I mentioned lung cancer as an example. This is a disease where patients will die very rapidly without treatment. The death rate's up to 4% per week while patients are waiting to get started on their treatment after being diagnosed. our only access to genetic testing was through academic sites. And to send that tumor material, that biopsy or that piece of cancer that had been removed to an academic site and then get an answer back took over 2 months on average for all patients. When we started doing gene sequencing in-house, that number fell from 2 months to 3 days. That when we first did that, that was a global record. It had never been done so fast in the history of the world. That was in 2020 that we first insourced the testing, and it's actually still a global world record today. The research department was integral in bringing this in. Research really helps us embrace those new technologies where we might need to hire new people, buy new machines, and it was very it can be very difficult to do that in a clinical department. And when the research department partnered with our laboratory department, it helped us overcome a lot of those barriers that can prevent clinical teams from making changes like that.
Hmm.
So having the Research Institute here locally really helped bring in what was a powerhouse service to the community of Brampton and the surrounding areas. And that helped us build the biomarker service, which in turn was integral to other cancer services. So from that, we saw, I mentioned the screening program that took off. We've had clinical trials for a number of targeted therapies that have opened as a result of that. And then we've also had additional collaborators wanting to work with the William Osler. So that's spread out our reach further beyond the community to other research sites within Canada, as well as around the world.
I find it so interesting that you started off talking about how the particular branch of research that where you're working, you're a little bit disconnected from other doctors and from patients to a certain degree. But when you talk about these connections, it's very clear that you are deeply connected to the way you are changing people's lives. And we've been talking some about kind of the scientific mystery and the medical mysteries that you're dealing with. But I think in addition to the revolution in knowledge creation that you're a part of, what does it feel like to also know that you're a part of a revolution that could help many, many people live longer, better lives? What's that like?
Um, it's been a really amazing feeling. It's a very gratifying way to work, and I think that really speaks to the powerful duality between medicine and research. Um, the job of a pathologist in the medical space can be a little bit lonely. We're not seeing our patients that often, and we're definitely not seeing our clinical colleagues as often. But when we combine that with doing some research really helps bring everybody outside of their traditional roles within the hospital. It reintegrates us into new teams. It really helps with that multidisciplinary collaboration. And there's a number of other benefits too. It actually helps take us around the world to meet colleagues from other hospitals. While we disseminate our own findings, it actually helps us learn about what other people are doing too. And so when we have the goal of telling people what a great job we've did, we actually come home with 17 more new ideas that we've got to take into action. And so I think that it's been really fortunate to get to play such an important role, not just on the clinical side, but in the research space as well. And with the formation of this new institute at the William Osler, I'm really excited that so many other clinicians are going to have a similar opportunity to help their work go viral and spread it all over the world.
It's fantastic. I am going to ask one or two more questions, but I just wanted to note that there is a Q&A field in the Zoom window, and we'll be taking questions from audience as well. So if people want to put their questions in there, we'll try to get to as many of them as we can. Um, so, but to come back to our conversation, uh, do you want to talk a little bit about what a biomarker is, what they tell you about patients and cancer. Um, I think that might be just an interesting thing to help clarify for people.
Yeah, absolutely. So we use this word biomarker. It's very generic. It's like kind of like saying what's up or any, it's a greeting, it's a adjective, it's a noun. Um, but really a biomarker is any piece of data that we can use to give a clinician a hint about what's going on inside of the patient. And whenever I define biomarker, I always think of the best biomarker in the history of all medicine is the pregnancy test. If a person walks into our hospital, it's really critical that we know if that person is pregnant or not. The easiest way would be to look inside of them. But our patients don't like that. Fetuses don't like that. It's a problem. So we have this really easy test called the beta HCG. In fact, it's so easy that patients can buy it themselves on the shelf at the drugstore. It's accurate to 99.99%, and it works within 1 minute. It can be a very long 1 minute, depending on if you're what your state of mind is when you're reading that test, but it works within a minute. That's one of the fastest turnaround times and most accurate biomarkers we can ever get. So when our oncologists or surgeons have a question about what's going on inside of their patient, and they don't want to have to open their patient up to get the answer, we tend to turn to a biomarker to try and give them as much a clue as we can about what's happening on the inside so we can plan their treatment and therapy in accordance. And whenever we develop a biomarker, we're trying to make it as accurate as we can and as fast as we can. And just remember that pregnancy test as the real gold standard. We're always trying to build something as good as that stick with the blue lines.
So I am going to go over to audience questions in a minute, but before I do that, I thought maybe we could take a look ahead. You talked a little bit about how we're in the middle of a revolution right now, that the technology you're using now is as revolutionary as the microscope was in its day. And when you think ahead both in terms of sort of general genomics analysis, but also in this idea we talk about of personalized medicine, we can keep it to cancer treatment in this case. How far can this go? How personalized can it get? How targeted? What can we look forward to?
So, one of the tests that we're now offering at William Osler, and I'm really excited about this, is something called liquid biopsy. Liquid biopsy means that instead of getting a small piece of that cancer, or taking a piece of tumor that a surgeon has removed, these can be difficult procedures for patients to endure, and they're not always possible to do safely. But we can now take a tube of blood from any patient and look for little bits of DNA that are circulating around the blood that might have originated from the cancer. And we can do ultra deep or ultra powerful gene sequencing and isolate those few fragments so that we can give our doctors information about the tumor without them needing to perform an invasive biopsy. That technology is becoming widespread around the world and is really the next big thing in terms of cancer care. I'm really excited to say that William Osler was the first hospital in Canada to have this technique available in-house, and that our doctors have been using that for the past 3 years. We've just finished a major study on the implementation of liquid biopsy here at William Osler, and that's been provisionally accepted for publication. Champika Nicholas is our lead author on that, so we're very excited about that study, which will hopefully be available to readers in the next few months or so. That is a really groundbreaking and game-changing technology as it enables precision medicine and personalized cancer care to be delivered to so many more people as before it required that surgery or invasive biopsy, and it's now no longer going to be a barrier to those patients who can't get through those particular procedures.
Hmm.
In terms of what's next for us, The offering now at William Osler is significantly ahead of what we're seeing at not just other community hospitals, but even academic sites around the country. So for our team, as far in terms of our advocacy and our desire for improved cancer care, not just in our hospital for our patients, but for the world and this country, we're really going to focus on our ability to transfer that knowledge. And we want to try and help get technologies like this ultra fast turnaround time or in-house liquid biopsy. We want to help other hospitals find a way to deliver this to their patients as well. So there is a gap now between what's available to our patients at Osler and what's available to others at outside centers. And I think closing that gap would be a really important role to play. In terms of what we're cooking up next, we are always looking for the next biomarker. We do have a few that we're looking to roll out over the next 2 to 3 years, but you'll have to stay tuned to see what those are, and perhaps invite us back for another research talk to see what's happening there.
I will certainly stay tuned. Okay, so maybe we'll give you some of the questions that the audience is wondering about. One question that has come through is a question about disparities in access to personalized cancer treatments. You've been talking about some of that, but again, it comes back to this idea of the community that you're a part of. For underserved communities or regions or people from marginalized groups, what in your research will help with that kind of equitable access? And are there specific things you're doing to ensure equitable access?
Yeah, this is a huge problem in Canada, in that we see major differences in cancer treatment based off of where a patient lives and what hospital they present to. So some technologies that are available to patients at Osler are just not available to patients at other hospitals. Um, Osler for cancer care started off on the bad end of the spectrum, and I think that we've really transitioned over to the opposite side. But there are still many sites that cannot get appropriate access to genomic testing. It's really based on where a patient lives and where they do present. Our group did lead another study. This one was led by Cassandra Bison, together with the Canadian Pathology Quality Assurance, or the CPQA. And in this study, we sent fake cancer samples around. These were colon cancer samples that we sent to all the major testing sites around the country. We asked each hospital to prepare a biomarker report for each case of colon cancer, and then in turn gave those biomarker reports to oncologists and asked them to prescribe a treatment. And what we found was there was a huge range in the time it took to provide these reports, ranging anywhere from a few days to over 2 months. And then there was a huge range in the quality of the reports. Some of the results were off. That was rare. But what was more frequent is to have a correct result with very poor communication, such that the oncologist did not really understand the genomic findings that were attempted to communicate through that report. And as a result, they prescribed the wrong treatment. So what we're seeing is that patients with the same cancer may actually get a very different treatment depending on which hospital they go to in Canada. That is something that we're going to have to address as a community. It's going to have to be us as researchers, as clinicians, together with our government and our decision makers are really going to have to do some work to try and increase the equity in cancer care in this country. And I think the challenge for us is to meet at the highest bar. It's one thing to say we have equitable cancer care, but we want equitable and good cancer care, which is a little bit more difficult to achieve.
And it sounds as though that question of equity has to do with more than just the research itself. It has to do with patient engagement, communication, a whole range of things, top to bottom through the process.
I think so. Just speaking to that community, research has really done wonders in terms of connecting those different groups together. And we've been really lucky to have strong partners in this mission. And a number of industry partners have really helped. They've really stepped up to fund a lot of this research to make it possible where it wouldn't have been. And then also our patient advocacy groups, so groups like Lung Cancer Canada, Colorectal Cancer Canada, and others are really doing their part to support this research and not just support it, but to be an active participant within this. We saw a recent paper from the group CRAN, CCRAN, uh, discussing the disparities across Canada. Um, and they really articulated that very well. And it's really nice to have patients contributing that type of research to what's available.
I'm going to move to another question now. You've been talking about one technological and research revolution. This crosses over with another. Is there a role that AI can play in the future of genomic sequencing and identifying biomarkers or identifying treatments and that sort of thing? Is this something that's on your radar at all now?
Um, yeah, of course. I mean, it's that's a hot topic, right? The honest answer is right now, no. That in a patient's cancer treatment in 2024, we're not using any AI, just I. And but we remain receptive to that possibility, and that's something that we're scanning for when we go to conferences, when we do our continuing education, just perusing the internet. We're just looking for ways that might change. But at the moment, no, we're not using any AI in patient care.
Right. Okay. Um, Another question that we had from the audience was, is there any targeted treatment or sequence having to do with pain management in cancer? Is that something specifically that's a part of your research?
So, absolutely. It's not a part of my personal research or the work that our group is doing, but precision medicine applies to every sphere and every aspect of care that we get. So, um, when we prescribe a drug, if we can hone that prescription based on an individual's genetic makeup, that's called pharmacogenomics, and that already is here. We've seen our first pharmacogenomic tests being done here at Osler. At the moment, not for pain, but there are certain gene mutations that a patient can carry, which would change the way they metabolize pain drugs like codeine. And so, knowing if you're a fast or slow metabolizer of these compounds can really help get a patient onto the best prescription, and it can even help avoid potentially dangerous scenarios with that prescription, like in breastfeeding.
I, I want to follow up on that just a little bit more. And I ask this partly because I have a son with an autoimmune condition who's been through genetic analysis to see how he metabolizes various drugs and metabolizes some of them in a very unusual way. How much variety is there in the way people react to pharmacological treatments?
Yeah, so I'm not a pharmacist. It's not my expertise, but we're always told that the difference between a poison and a treatment is just the dose. And the way we figure out our dose has to do with our size, our total body surface area, as well as the volume of blood that we have circulating. It's very hard to customize that to an individual person. Having a little bit of data about how our liver enzymes work and if we're known fast metabolizers or slow metabolizers would be very helpful, but it has to be taken together with other factors. And like all areas of medicine, the genomics is just going to be one piece of the puzzle. And we're going to have to put it together with everything so that when we prescribe a treatment for a patient, whether it's a cancer treatment, pain relief, or anything, that we can be really confident that this is going to work, it's going to do what it's supposed to, and that the side effects are going to be minimal. And where there are side effects, we can predict what they are and counsel patients for how best to deal with them.
It's very interesting with all of this that often when we talk about cancer, people have the initial fear of the cancer itself, but also people are aware that cancer treatments can be an ordeal. So all of the things that you're talking about feel like they demystify that and take some of the fear out of that, replacing it with knowledge. So I think that's extremely valuable. The next question that we have, it has a little bit of a preamble, so I'm going to read it verbatim. It says, it would stand to reason that formal molecular pathology training is required to prepare for system-wide transition to modern cancer care. However, Canada does not have formal training in this area. We can't expect to scale if we don't have molecular pathologists ready to support clinicians. And then the question is, what can patient organizations do to help? And what are the professional organizations doing to help?
Okay, so let me just explain a little bit about where that question is coming from to some of our audience who doesn't have all that background.
Right.
Is that so and I think this actually goes back to your very first question, Patchen, is that what school did I go to get here? And if to become a pathologist, you have to go through medical school. And after medical school, you do a residency. And for me, I did a residency in laboratory medicine. After that, you can become a molecular pathologist either by doing training in the US or just simply declaring yourself a molecular pathologist. We have no formal training program so that if somebody can get a diploma in this that's recognized in Canada. One of the ways that a lot of Canadian sites have been held back is that they don't have a molecular pathologist, and that in many other hospitals, instead of using a pathologist, they'd be using somebody with less training to do a similar job, and the effects can be less than desirable. It- that is something that we're going to have to embrace as a nation. And I think that having a recognized specialty of molecular pathology is really going to help. Just establishing the field as legitimate will help draw more talent into the profession and can really help build that precision medicine portfolio that we're looking to have here as a country. Now, that being said, formal training is one thing. I think that there are a lot of individuals whose passion combined with their skills can really step out of the woodwork to make amazing things happen. And when you look out for those, you can really facilitate precision medicine even without formal training. I think one amazing example would be here at William Osler. Our advanced diagnostics division provides all the biomarker testing for our hospital as well as several other sites around the province. And leading that service is Andrea Bihari. Andrea is her background is in immunohistochemistry. That's a
Hmm.
really fun word to say. It sounds super sciencey, immunohistochemistry. You can practice it. It took me a long time to get there. But she was doing amazing work doing ER, PR, HER2 tests like that, our IHC or immunohistochemical tests, and providing those for our breast cancer patients, for our surgeons. And she embraced the idea of providing this new technology. She saw how important it was, how it could completely change the narrative for a patient and for an organization. And she just decided one day to learn it and very quickly became one of the best providers of NGS in the planet.
Hmm.
So, to anybody who says you need formal training or a diploma on your wall, I always think of Andrea Bahari and the amazing things that she's been able to do for her patients, simply by paying close attention and having that strong passion and that desire to do right.
I've noticed there's a related question here, which is whether you have any advice for students, current students who might be interested in getting into this area of research. Do you have any practical or emotional counsel about how to proceed?
Oh yeah, stay with it. It's a very long journey. I think that for students interested in research or healthcare, there can be a lot to discourage you when you're at that undergrad phase, when you're in high school. I think the way admissions work in medicine is just frightening. But if anybody is interested in this, just keep going, keep keep persevering, do what you believe in, and if you have that passion, and it will fuel your energy, and you'll be able to keep going and going. Eventually, you'll get to where you've got to go. I think that that passion is the most important thing. It's more important than any skills or diploma or anything else that you'll pick up along the way.
And now shift. There's a question about um, we've all heard much about mRNA vaccines over the past 5 years or so. And one of the places where you hear about potential is in cancer prevention. So is this something that's part of your research, or is there anything you can talk to about the role of mRNA vaccines in cancer prevention?
So it's this isn't part of my research, and I'm not an expert in it, but through the pandemic, we all learned how to talk about things like this, even though we're not experts in it. So I'm happy to give a little bit about it. Um, DNA, RNA, and proteins are the basics of cell biology. Where we find them uh, in human cells and cancer cells, even in viruses. So, ability to understand these molecules, to create new molecules, to target these alterations, our ability is just getting better and better and better. We saw probably a little bit too early the rollout of mRNA-based vaccines, but nonetheless, I think over the next decade, these are going to become a very powerful part of cancer care. But all spheres of medicine, including infectious disease as well.
Okay. We have to unfortunately wrap up in a couple of minutes, but I've got time for one or two more questions. There was a question following up on what you were talking about with liquid biopsies and that incredible advance. And the question was, is there a role for patient advocacy in driving its adoption so that more people can benefit from it?
Yes. In fact, patient advocates are the most important advocates. We saw that. So I mentioned that lung cancer is the number one cause of cancer-related death for Canadians. That's true today. But if you were to go back 30 years ago, the number one cause of cancer-related death was breast cancer,
Mm.
particularly for Canadian women. And breast cancer patients have done an amazing job with their advocacy, where we saw personalized medicine hit breast cancer patients first in the late 90s with estrogen receptor and HER2. We've seen phenomenal strides in terms of the screening and early detection. We're about to start screening patients earlier now, as early as 40 years old for breast cancer in Ontario, which is an amazing step forward. All of these things happen because of the work that advocates do. And it's not the politicians or the doctors, it is patient advocates. So anybody who's been affected by this disease, it doesn't matter if you've personally been affected or if it's been a family member, your voice is incredibly powerful. And having that patient voice supporting us and backing us up when we go to our ministries of health for resource is absolutely critical. All the work that you see here at William Osler, including liquid biopsy, including rapid NGS, is all possible because we've had strong patient advocates who have been working in close collaboration with our research and clinical groups.
Fantastic. Okay, we have time for one more question, and it's a pretty good one to wrap up on. The question is, we talked about the future of the research, but this question is, what is the future for Osler and the Research Institute? And the question is, will it become a cancer center?
Yeah, so well, I'm happy to announce Osler's already a cancer center. And cancer center is a state of mind. It's all about the work you're doing, what you're providing to your patients right in front of you. And we are absolutely delivering cancer center care right now. uh, we have so many exciting endeavors in the future. Tiziana mentioned several of them in the introduction. We're transforming to become an academic health sciences center. We're going to be partnering with a new and exciting medical school that'll be opening its doors next year. We have our research institute, which is really going to take the types of things that we've been talking about today and make them more accessible so that we can see these sorts of developments in geriatrics and diabetes care and nephrology, and really see that excellence in clinical care take hold in our community. And yes, there will be a building with the formal words Cancer Center going up in the parking lot facing Beauvert Drive. We absolutely cannot wait for that. And truly, we can't, because it really doesn't matter that the building hasn't gone up yet. Like I said, cancer care is happening right now. We are offering precision medicine. We have a suite of clinical trials so that our patients can actually access medicines and treatments that are novel and not available in regular centers. And that's all thanks to a lot of the hard work that our research department, led by Dr. Chima, and her amazing ability to take on these clinical trials and support an offering that is over more than double what a hospital of our size would typically be able to support. So the future for William Osler is incredibly bright. I I can't wait to see these multi-year projects like medical school and cancer center and research institute finally taking form all at the same time. Is really just it's been incredible to be a part of this energy, and to see our community hospital emerge as a world leader in healthcare has been one of the most gratifying and rewarding experiences that I think any doctor or researcher could hope for.
Well, I want to finish just by congratulating you on that research and thanking you for a really illuminating discussion. This has been just fantastic. So thank you so much.